take a look at your thermodynamic activity and try and work through that. Okay, this right here just asks you, not looking at values, whether the entropy is going to get greater or smaller for these process. That's all you're doing. You're just putting plus or minus. Okay, this one right here, you just have to circle which chemical has the greatest entropy, depending on the chemical formula and the phase. That's all you're doing. This question right here, this is your activity. You need to look at this reaction. You need to find delta H, delta S, and delta G, so you can calculate these values, because that's what it's asking. And then you can calculate free energy using delta H minus T delta S, and then find free energy using products minus reactant. Okay, and then answer whether this particular reaction is spontaneous or not. This one right here, it shows you that for this following reaction, hydrogen cyanide is being produced, that's HCN, and in the reaction, is the reaction spontaneous at high temperature or low temperature? And this is related to the discussion in lecture on temperature dependency. So I'll talk to you guys more in detail about temperature dependency of free energy next time, but I just want you to be aware of that. So if you can complete this particular activity for next time, then you're good to go. Okay, this one, for each one of these reactions, calculate delta H, delta S, and delta G. There are 4 reactions that you guys need to do that. So that's basically products minus reactant for delta H, delta S, and delta G. Use the appendix in the lab manual. Why? Because I find out over the years, the books are not consistent, okay? The values that I give you in the appendix in the lab manual is based on the book that we are using. But if you look it up online, the values are going to vary. And so when we're grading these things, your numbers may not match to my key if you're using different values. So always use the appendix in the lab manual when you're doing these calculations. That way we're consistent. The numbers aren't as important as you guys understanding how to do the math or to do the calculations. But in order for me to double check to make sure that you're doing the calculations correctly, I need you to use the correct numbers, okay? So the rest of these questions really pertain to this right here. What I will ask is, which equations are endothermic? What you need to do is you need to look at delta H for each one of these equations and see which ones are positive. Whichever has positive delta H are endothermic. I might ask you, which reactions here gives you a higher degree of order in terms of entropy. So what you want to do is look at these equations and find your delta S and see which ones are negative. Which equations are always spontaneous no matter what the temperature? You would take a look at delta H and delta S and see which ones will not change but gives you negative delta G no matter the temperature. So that's why you need to set up this table right here so that you can answer the rest of these questions. I talked to you guys briefly about this, but some of you, of course, are not on my lecture. So what I want to do now is I want to, let's see, I want to share my screen and show you. So it's about thermodynamics and understanding the different aspects of thermodynamics. When you think about thermodynamics, the ultimate question thermodynamics tries to address is whether the reaction or process will occur. So the question to be or not to be, the answer is it spontaneous or not spontaneous? Spontaneous meaning that it'll just go as is depending on the conditions you have. Not spontaneous means that maybe you need to put in a little bit of work, a little bit of energy to get that reaction going. And some reactions, no matter what you do to it, are never going to happen, okay? Some reactions, you can get it to happen even if it's not spontaneous by changing the conditions, generally the temperature. So that's what we are looking at in thermodynamics, Okay. When we're addressing the question to be or not to be, will the reaction occur or not occur, we have to weigh two factors, two state function. The thermodynamic parameters that we are covering are called state function. Why are they state functions? Remember what state functions are. State functions are functions in which only the end and the beginning is the information you need to calculate the value. Okay. Like for example, the distance between San Diego and San Francisco. If you know the distance between that, then that's a state function, because you can measure the beginning, San Diego, and you can measure the end, San Francisco, and then that difference, of course, is going to be the distance. But traveling between here and San Francisco is not a state function. You can fly, it'll be short. You can drive, you can pedal, you can do whatever, different modes. So that's not a state function, because the path by which you go about that process is going to depend on how much work you put in, how much energy you put in, how much time it takes. Okay, so that's not a state function. State functions like entropy, free energy, even electrochemical potential, since we're covering that, and enthalpy are state function. All you need to know is the beginning and the end. And that's what this particular graph shows you. In order to figure out whether this reaction is endothermic or exothermic, you need to know the energetics at the final state and the initial state. Once you know the energetics, and we covered this in kinetics, remember, final minus initial, we get delta H reaction, then you can get the enthalpy of the reaction. You can also do so if you know the entropy. And you can also do so if you know the free energy. But the path by which you go from the initial to the final, that will determine how fast this reaction proceeds. Now, sometimes the reaction is not very spontaneous. It could be an endothermic reaction. So endothermic reactions are generally not spontaneous in terms of energetics, because it's uphill. Now, the driving force of whether that reaction will occur or not is the other factor, entropy. There's two factors at weight that you have to consider whether the reaction is going to be spontaneous or not. One is the energetics. The other one is entropy, okay, the chaos. And we'll talk about that shortly. For those of you in my lecture, it'll be good review. It'll be good review. But the way you get there is going to depend on the activation energy. Now, it may be unfavorable, okay? Maybe a reaction is endothermic, unfavorable, and maybe the entropy, yeah, it's positive, but not that positive. So the question is, if you make the temperature higher, then you certainly will be able to get more molecules to the other side. And the question is, well, if the reaction is unfavorable under higher temperature, why would you use higher temperature to drive that reaction? And the reason why would be, yeah, it becomes less favorable. Delta G becomes more positive, but you also got to look at the economics. If you can get more material in a less amount of time because of the kinetics, then you do so, okay? You sacrifice the efficiency for the fact that you can get more for a certain amount of time. So you have to not only thermodynamics, you look at delta H and delta S, but in terms of overall economics, you look at thermodynamics and kinetics. Kinetics allows you to get your product quicker. Thermodynamics just allows you to get your products with less cost, less energy input, okay, if it's temperature dependent. So think about that in some of the questions in today's activity. So we talked about that. I want to talk, like I said, there are two things that you have to consider when you think about spontaneity. One is energetics. Whenever something is downhill, things will naturally fall. Things will naturally fall. That's the state that objects like to lie. They want to go from a higher energetic state to a lower energetic state. That's a spontaneous process. Things do not spontaneously levitate, Okay, it just doesn't. That's not working here on planet Earth. That's not the spontaneous process. But we can get things to levitate. We can get the reaction to go in the endothermic reaction process if we weigh the other factor, entropy. Okay, entropy. And that's what we're looking here. The greater the entropy, the more likely that process will occur. And what exactly is entropy? Entropy is a measure of chaos. More specifically, it's the measure of microstates. So here, what we have is, here you see all kinds of chaos, and that's what nature prefers. In fact, that's the second law of thermodynamics. Nature prefers a universe that has maximum entropy, okay? But in terms of the mathematics, entropy has to do with available microstates. The more available a microstate is, okay, a system has a way of going from one state to another, its product. And the product can be arranged in different ways, okay? And these different ways, these different scenarios are the states or microstates. And the more microstates that are available, that's the most likely outcome. It's like trying to win the lotto, okay? There's only going to be, what is it these days? I haven't played that thing in years. You got to get all 5 numbers correct, okay? So there's like one in so many millions of chances. Well, that sequence of number is only one microstate in millions different arrangements. And so the chance of you winning the lotto is more likely to occur than you winning the lotto. Now, it's not an impossibility, but it's highly improbable. Okay, that's what we like to say in chemistry. So in terms of the scenario that you see here, you see there are 4 gas particles in 2 chambers that are connected by a tube, and it's evacuated. So these particles are free to roam. And so what are the different arrangements? Well, the different arrangements is that all 4 particles are on one side, or 3 of the 4 particles is in one side and 1 particle is on the other, or 2 particles is in both sides of the chamber. What are the probabilities of these different scenarios? Well, 4 particles on one side, at least to the left, that's 1. 3 particles on the left, 1 particle on the right, that's 4. Okay, 2 particles on each side, that's 6. Now, if we take this and break it up to this right here, okay, so this is 1, 4, 6, but then we have to look at the other scenario in which the 3 particles are in the other side. So that's 4, and then this is 1. But the highest probability of occurrence is when both chambers have 2 particles apiece. So that's going to be the state of the greatest entropy, because it has more available microstates. That's what we mean by entropy. Okay, more available microstates. That's in mathematical sense. And nature prefers that we go to a state, we go to more microstates. That's the event that will occur. That's basically what entropy has. And so when we look at different systems, and this is related to your first question in your activity, and we want to see, okay, which one has more chaos? That's what we're addressing. Copper at 273, copper at 295, copper at 298. Well, temperature plays a role because temperature monitors molecular motion. And so anything above 0, the substance, the material, is going to start vibrating. And so when it's vibrating on one state versus the other, there's going to be more microstates of where that particular material is in space-time. Okay, when it's vibrating, it's going to be here and there. And the higher the temperature, the more vigorous the vibration. So the higher the temperature, the more microstates you have available. If something is slowly vibrating versus something that's highly vibrating, the thing that's highly vibrating, and then of course, as you increase the temperature, then it's going to be moving around as it goes from a solid to a liquid to a gas. So again, Which one's going to have greater microstates? The one at higher temperature, because it's going to have more energy, it's going to have more vigorous vibration. Which one has higher entropy, a solid or a liquid? The liquid, because the liquids are free to, they're not confined to the XYZ plane anymore. Yeah, it's vibrating in XYZ plane as a solid, but now as a liquid, they're tumbling. They're free from each other. And then gas, they're totally separated. So the gas is going to have a much more greater entropy than a liquid, and a liquid will have a greater entropy than a solid. Again, it's the way we envision these microstates. The gas, the different place these particles can be, is going to be more available more often than in the solid. It has a greater entropy. So of course, when we answer this question, we say that a 298 copper solid is going to have a greater entropy. Sodium, solid, liquid, or gas. I just said the gas will have a higher entropy. So here it would be the gas. For water, the gas as well. For carbon, it would be, if we can take carbon, there's two forms of carbon, diamond and graphite. Which one's more ordered? Diamond's more ordered. So graphite's going to have the greater entropy versus the diamond. Remember that diamond is tetrahedral structure in which carbon is bound to 4 other carbons. On the other hand, graphite is sp2. It's trigonoplanar. It's basically a sheet. That's why graphite is a really good lubricant, because what happens is that there's one layer of graphite, another layer of graphite, and they can slide amongst each other. So the carbon can move. So that's greater entropy. Okay, but if we were looking at graphite in the solid, liquid, or gas, of course, the gas would have a higher entropy. So just knowing phases and knowing microstates, we can predict which one's going to have the greatest entropy. Now here, this is a little bit tricky. What we have for these is the dissolution. So the dissolution is sodium chloride solid going to sodium ions and chloride ions, because that's what happens when something dissolves. Okay, and so which one's going to have entropy? The solid or the aqueous form? This is not liquid form. Of course, in the aqueous form, they're separated, but the water is going to be responsible for hydrating these ions, stabilizing these ions. So there's a degree of organization of the water to these ions. The question is the solid, sodium chloride, and the water more ordered than the sodium chloride ions being surrounded by water? Okay, and so that's something that we need to discuss, because it depends. In some cases, when you dissolve something, the entropy does increase. In some cases, when you dissolve something, the entropy actually decreases. Surprise. Okay, the entropy actually decreases. Why? Because the ions that forms are going to demand that the water be more ordered around it. And so the entropy decreases when we look at products over minus reactant. So we'll take a look at that and look at the results, and then we'll take a look at these as well. So what is the answer? Well, the answer is the following. Okay, here the entropy of 298 is greater than 295 versus 273. That's what is expected. Here, the entropy of a gas is greater than a solid. That's expected as well. Here, the entropy of the gas is greater than the liquid. That's expected as well. Here, the entropy of the gas is greater than graphite. Okay, graphite has an entropy of 5.7. The gas, graphite gas, 158. Expected. When we dissolve something from a solid and it goes into water, the entropy increases. That's expected. Here, the entropy decreases. So it goes from 150, 167 in the solid, but when you put it in water, it decreases to 158. In other words, the product, when aluminum chloride dissolves, it actually is more ordered. Why is that? Well, the reason is because of the charge of aluminum. Look at aluminum, it's +3. +3 cation is going to demand that the surrounding is highly ordered, because the +3 is going to demand that. So because it's highly ordered, there's more organization there. okay, to a higher degree than just sodium chloride alone. That's why you get a negative entropy. It's more ordered. So in that particular case, okay, when you're looking at dissolution process, when you have a positive 2 cation, it can go either way. It could be more entropy or less entropy. Positive 3 ions is definitely going to be less entropy because of the water dissolution process. So for that, if you're really not clear as to whether the entropy increases or decreases, you could easily look it up on a table. Okay, and what is that table? A table that looks like this. This is found in your appendix, and in the thermodynamics data, this is it right here. Okay, and what you can do is look up aluminum chloride. Here's aluminum chloride. You can see the entropy in this particular case, or is, that's a solid though. That's a solid. That's 109.3. It doesn't give you the aqueous, but the aqueous would be a negative. Okay, that would be a negative value. I don't know if that's found in your book, but here you got to remember that that's a solid. This particular question was this right here. Okay, that's aqueous. It's different from solid. So keep that in mind. When how would you write that reaction? How would you calculate the entropy? You would look up aluminum aqueous, which isn't here, but you would do that. This is the reaction that you guys would have wrote. Aluminum chloride solid. Oops. If you were asked to calculate this, this is what you would do. Aluminum chloride solid. You can get the entropy from that. Going to aluminum plus 3 aqueous. You can figure out the entropy for that, plus 3 chloride ions aqueous. So products minus reaction, products minus reactant for that would actually give us a negative 148 joules entropy. Okay, that's why it's negative, because the hydrated ions are more ordered because of the water than just aluminum chloride alone. It's not logical, but that's the reason why it's negative. So for any reaction or dissolution in which you have a charge that is generated that is +2 can go either way. +3 definitely is going to be more ordered. Okay, so if it's +2, try and see if you can calculate the value. I don't think I asked you a question like that, but if you had a choice. So let's move on and let's take a look at this right here. That would be fine. This is methanol. Methanol can hydrogen bond. So methanol can be in the liquid state, pure methanol, or it can be mixed with water. And when we mix it with water, we can see that the entropy goes up. In its pure liquid state, it's more ordered versus water, even though it hydrogen bonds to water, methanol. Gas diffusion. Gas diffusion is the gas or the gas being dissolved. You can see right here that the gas being dissolved is going to be more ordered than the gas, the oxygen as a gas. Again, the gas is going to have the greatest entropy because it has more microstates. Okay, when all things are the same, you got both solids, the reaction is the same, then look for complexity to determine your entropy, which one's greater, which one's lower. Complexity has to do with the number of atoms in a molecule. The more atoms in the molecule, the more ways you can rearrange those atoms in three-dimensional space. If you're just looking at atoms, the more electrons and subatomic particles you have for a particular element, the more entropy it will have, just because the electrons are free to move around more randomly than an element with less electrons. So here you see lithium, sodium, potassium, rubidium. Rubidium is going to have the greater entropy. Why? Because it's a bigger atom. So these are just examples that will help you answer the first question of your activity. And the first question of your activity is basically, if the product has more available microstate, the entropy goes up, you would put positive. Does the product have is more organized compared to the reactant, the entropy would go down. You put negative. And then here, these are the questions that I was just asking. You look at these three systems right here. You have aluminum, sodium chloride, calcium chloride. Which one will have the greatest entropy? I think we asked this. Here we have methane, propene, and this C2H6 is acetylene. Which one has the greatest entropy? They're all in the gas state. Okay. And then here we have lithium nitride, lithium oxide, and lithium bromide. Okay. I think in this particular case, what I've tried to do is, again, they're all lithium compounds. You should be able to figure out which one has the greatest entropy. Again, you got to remember that, yeah, if you have a bigger element, you're going to have more entropy because that complexity. But if you've got more particles, that's even greater entropy, because even though you might have a bigger element, you only have 2 versus elements where you have 4, and now there's different ways of arranging. So you should be able to answer this particular question. Okay. The second law of thermodynamics is really how you address this question, to be or not to be. Is it spontaneous or not spontaneous? It goes to the second law of thermodynamics. Second law of thermodynamics simply states that the entropy of the universe is always increasing. It's not conserved. Unlike the first law of thermodynamics, first law of thermodynamics simply states that the entropy, the energy is conserved. You can't create or destroy energy. You can only convert it from one form to the other. Second law of thermodynamics states that the entropy is always increasing. It's never conserved. It doesn't stay constant. It is always positive. So what we can do is we can take this entropy of the universe and rearrange it so that we can just look at the system and not the universe. And when we do that, we get this equation right here. Okay, this is in the lecture notes. Entropy of the universe times T is this new state function, which we call free energy, delta G. So remember that delta S of the universe is always positive, so that's spontaneous, but there's a negative in front of that. So a positive delta S of the universe is a negative delta G. Okay, it's a negative delta G. So basically negative delta G is positive delta S, that's spontaneous. When delta S of the universe is 0, it's like delta G is 0. When delta S of the universe is negative, which is not spontaneous, it won't happen. The reverse is going to be the spontaneous process. That's like delta G being positive. Okay, and how do we calculate? Well, you can use this mnemonic device to figure out if delta G is negative, then the forward reaction is the spontaneous reaction. If delta G is positive, then the reverse reaction is the spontaneous reaction. And if it's 0, it's sitting down here at the bottom of this bowl. Okay, and this is the reaction that we have that relates free energy, which is related to the entropy of the universe, to the enthalpy and the entropy for a system. Okay, now I want to go ahead and move forward. You can calculate free energy either through T minus D. Free energy equals delta H minus T delta S, or you can do products minus reactant. There's 2 ways of calculating free energy. In fact, there's more than 2 ways. There's a number of ways because free energy is so important. So here's an example. I have this reaction. It's basically the combustion of methanol. Methanol and oxygen produce carbon dioxide and water. What is delta G for this reaction? Well, if you want to do products minus reactant, then find these values in the appendix right here. You need to look for methanol. So you would look for carbon, because that's the main element in methanol. And you would find C2H3OH. Look up methanol, C2H3OH right here. And you notice that it's both in the liquid state and the gas state. You got to make sure you pick the correct state. That's why the phase is important when you write this reaction. Well, in this case, it's a gas state. So you want to pick this value for delta H, 82.9, this value for delta G, and this value for delta S right here. Okay, these values right here, because we're looking at the gas state. We're looking at the gas state. Minus 201, I mean, minus 161.9 and 237.6. And that's what we have right here. Okay, and that's for methanol. And then you would also look it up for oxygen and carbon dioxide and water. You have to use this table to find those values. But the calculation is not difficult. Once you do that, here they are for all these chemicals as found in the table. Then you can calculate products minus reactant. It's always final minus initial. Products is your final chemical in a reaction. Reactants are your initial. So always final minus initial. And when you do that, you get a minus 1351.88 kilojoules. This is kilojoules. Positive 92.32 joules. Entropy is in joules per mole or joules per Kelvin. We already took care of the moles because we multiplied by the coefficient in the balance equation. Notice the two have different units. One is kilojoules, the other one is joules. So when you combine it, make sure that you convert one to joules or the other one to kilojoules. Otherwise, you're going to get messed up. That's a common mistake that I see. So if we can use that right there, by the way, without doing any calculation, a combustion reaction is always exothermic. It always generates heat. That's consistent with that negative sign. Combustion reactions are always exothermic, no matter what. And then if you look at this reaction, we have 5 particles in the reactant, 6 particles in the product. Entropy increases because you got more chemicals in the product. So delta S should be positive, and that's what you see right here. So before you even do the calculation, you should have an idea of the signs of both delta H and delta S in general. Okay, then we can do the products minus reactant. I mean delta H minus T delta S, and this is what we get. And if we compare that to delta G, products minus reactant, this is what we get, and it's pretty close. It's difference by 1/10 of a kilojoule. Okay, so again, I want to write this right here. Delta G equals delta H minus T delta S. This is important because when delta G is negative, that's spontaneous. It can only be negative if delta H is negative and delta S is positive. Under that condition, when delta S is positive, and if you think about it, things becoming more chaos is spontaneous, and things that are always decreasing in energy is always spontaneous. So together, those two concepts, without even looking at the signs, suggest it's going to be a spontaneous process, no matter what the temperature. Things that are more chaos because of the second law of thermodynamics and things that are downhill energetically, always spontaneous. On the other hand, the opposite is true. If the energetics is always uphill, uphill's not a spontaneous process, and you get more organization. That's always going to be non-spontaneous. Always going to be non-spontaneous under any temperature. So for this sign right here, spontaneous and exothermic, delta G is always, well, matter the temperature, negative, spontaneous. On the other hand, because remember, a negative here and a positive here makes that whole thing negative, and a negative plus a negative is more negative. Okay. On the other hand, if our entropy is more organized and our enthalpy is endothermic, then this will always be positive. Always be positive. When the signs are the same, delta H and delta S are both negative, or delta H and delta S are both positive, then the temperature defines the spontaneity of that reaction. And this is what we have right here. Okay, let me just move on from this. This is what we have right here. This is just an example of spontaneity in terms of phase change, but take a look at this right here. This is what we have right here. This is just an example of spontaneity in terms of phase change. But take a look at this right here. We've already talked about that, but suppose both of them are negative. So in other words, the reaction is exothermic, but the entropy is more organized. Which one is going to determine free energy? Well, that's where T comes into place. At low temperature, this becomes the dominant species because a number multiplied by a small number is going to give you a very small number. So this is going to be negligible at low temperature, and delta H dictates the direction of the reaction. Because it's exothermic, delta G, therefore, at low temperature will be important and the reaction is spontaneous. But as the temperature starts to creep up, then T delta S becomes more bigger than delta H, because a big number multiplied by entropy now overcomes the enthalpy value. And so at high temperature, okay, this becomes the dominant term, this becomes negligible, and then because delta S is negative, a negative and a negative, remember, a negative and a negative makes that a positive, and a positive delta G is not spontaneous. So when they're both negative, low temperature favors spontaneous reaction, high temperature favors non-spontaneous reaction. When they're both positive, that's what you see right here, okay, then what happens again, at low temperature, this becomes negligible because a low temperature means you're multiplying by a small number. And the enthalpy, the fact that the enthalpy is endothermic means that it's not a spontaneous process at low temperature. On the other hand, at high temperature, T delta S now becomes significant. And because this is a positive value, a positive times a negative makes that more negative, that T delta S becomes more dominating compared to delta H. And so now the positive delta S and the negative in front of that makes that a spontaneous process. The positive delta S and the negative in front of that makes that a negative delta G, which makes that spontaneous. The delta H is not a factor anymore because it's going to get overwhelmed. So again, you want to visualize this because you can approach it using the math, but it's much easier if you remember that there are two competing factors, entropy and enthalpy, okay? When both of the signs are competing or both of the signs are the same, then the reality is that both concepts are competing against each other in terms of spontaneity. When it's downhill but more organized, one says it's spontaneous, the other one says it's not spontaneous. Temperature plays a role, okay? Temperature plays a role. When it's uphill and more chaos, okay, then again, they're opposite. More chaos is spontaneous, uphill is not spontaneous. So temperature plays a role again, okay? Temperature plays, at low temperature, enthalpy is the dominant factor. At high temperature, entropy becomes the dominant factor. So I know it's a lot of conceptions that you guys will have to understand, but it's easier than the math that we covered in equilibrium, okay? So just try and make sure it's crystal in your mind in terms of how these two factors are dictates the value of free energy. That's one thing that you need to remember. Class, by the way, when delta G is equal to 0, and delta G is equal to 0 when we have a phase change. Delta G is equal to 0 at equilibrium. When does equilibrium occur? When a solid converts to a liquid. The phase change, the freezing and melting point of a substance. That's an equilibrium process. Or the boiling of a substance when it goes from a liquid to a gas, that's an equilibrium. Delta G is equal to 0 for that because it can go either way. Well, when delta G is equal to 0 and it's still delta H minus T delta S, you can actually figure out that temperature. in which it either switches from spontaneous to non-spontaneous or non-spontaneous to spontaneous. And that equation is this right here. T equals delta H over delta S. Okay, it's equal to delta H minus delta S. And in order for this to work, delta H and delta S have to have the same sign. They have to have the same sign, because if they're both negative, then that means T is positive. If they're both positive, that means T is positive. If one is positive and the other is negative, that means T is negative. There is no such thing as a negative Kelvin. There is no such thing as a negative Kelvin. That's why when you look at this right here, okay, when these things have opposite signs, it's independent of temperature, because there is no switching temperature in which it goes from spontaneous to non-spontaneous. It's either spontaneous all the way, no matter what the temperature, or it's not spontaneous all the way, no matter what the temperature. It's only when they have the same sign, it's only when they have the same sign that you have a switching temperature. And the switching temperature is the temperature in which it goes from spontaneous to non-spontaneous, or vice versa. This reaction right here is carbon dioxide and water gives you glucose plus oxygen. This is the reverse of photosynthesis. Okay, so in order to, before you even start this reaction, you guys know photosynthesis, right? A lot of you've taken biology. Is photosynthesis a spontaneous or non-spontaneous reaction? Do you need energy for that to occur or not? Okay, so what is the reverse? So before you start this problem, you should know the sign of delta H and delta S. And then just find these values, the delta H and delta S, in the appendix. Okay. Is the above reaction spontaneous in the forward or under standard state conditions? And again, you're just trying to confirm whether delta G is negative. If delta G is negative, it's spontaneous forward direction. This right here has to do with this reaction, okay? And yeah, hydrogen cyanide's there, but you don't need that value to calculate this. You just, the question is, why would you drive this reaction at higher temperature, even though it's not, the delta G becomes more positive, becomes less favorable at high temperature. And I think I talked about that. You don't need numbers on this. It's sort of like a qualitative answer. Give me a reason. Give me a reason. That's why I didn't think you need the thermodynamic data for HCN, because I don't reason. For this one, so just do products minus reactant for delta H, products minus reactant for delta S, and products minus reactant for delta G for 4 of these reactions. And then when you have these numbers for the reactions, then you can tell me which of the above reaction is exothermic and endothermic. For thermicity, there's only one thermodynamic parameter you're looking at. That's enthalpy. Okay, that tells you whether the energetics is going to be downhill or uphill. Which of the above reaction is spontaneous under standard state condition? When you're talking about spontaneity, you're looking at free energy. Okay, free energies is what determines spontaneity. If it's negative, it's spontaneous. If it's positive, it's spontaneous in the opposite direction. It's not spontaneous. Which of the above reaction could be made spontaneous by increasing the temperature? So in other words, the delta S is positive because could be made spontaneous. A positive entropy means that the higher the temperature, the negative T delta S becomes more negative, and then it becomes bigger than delta H. So think about delta H minus T delta S, what we just talked about. That's why I wanted to spend some time about temperature dependency, because then you can address these questions. Which of the above reaction will always be spontaneous? I think we talked about that in the last discussion. Which of the above reaction will become non-spontaneous by increasing the temperature? We talked about that as well. That's why I wanted to talk to you guys about the temperature dependency. That's really an important concept. of spontaneity. Okay, so that's basically your activity. That's basically